Okay, so now we're going to learn about body representations. So you'll see that a lot of times people talk about something called BREP. And this is basically body representation. So the body representation is how a computer, well, mostly how the software saves the progress of your files or your work. So first is going to be a file format. So when we go to AutoCAD, you're going to have the DWG, but if you go to SolidWorks, you're going to have the SLDPRT, solid part. And sometimes you can open software, you can open a part from a different software, but usually you cannot open AutoCAD drawings in SolidWorks, and you cannot open SolidWorks in AutoCAD. So when you create your part, which we're going to start designing on AutoCAD, say you created a cube. All right, so once you create your cube, AutoCAD is going to understand that as a set of curves and a set of lines. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8 points. So AutoCAD knows that you're going to have 8 points. And more complicated surfaces or bodies or solids will have more points. Right? So you have 8 points, and then AutoCAD also knows, or SolidWorks or the CAD knows that you have 1, 2, 3, 4, 5, 6. 6 surfaces. So a cube has 6 surfaces. All right, and all that between points and surfaces was created with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lines. All right. You can see that you have 1 here, 2, 3, 4 on this face, and you don't repeat the line. You're just basically using that same line here. So 4, 5, 6, 7. You don't use that. You go to 8, 9, 10, 11, 12. Okay, so you're having 12 unique identities. So 8 points, 12 lines, and 6 surfaces. This whole thing is one single body or one solid. Why? Because this has a volume. This thing right here only has coordinates, x, y, z. So each point has coordinates. Each surface has an area. Each line has a distance, coordinates from x1, y1, z1 to x2, y2, z3, z2, and x3, y3, z3 for every point. So what I'm saying is that if you have, I know this is pretty basic, but we have to understand this from the get-go. Otherwise, you're going to have some issues with body representations when you create solids. So x, y, and z, each point will have a distinct coordinate, and that depends on where you put your coordinate system. That is unique, and that is important because later when you go to mechanical engineering, when you go to electrical engineering, when you go to chemical engineering, architecture, where you place your coordinate system is very important. For instance, if you design an airplane, or I'm trying to draw an airplane here, probably not the best, but let's give it a go. Okay, so if you design an airplane, you're going to have to choose if you want your airplane to have the coordinate system here or your coordinate system in your mass, a center of mass. And you might wonder, why not anywhere randomly? Well, because if you want your coordinate system in your center of mass, that is very how do you say that, is very useful, is the word, is very useful, because then when you find the drag forces and the lift forces of fluid simulation, or even for manufacturing purposes, you'll know where the stress, the internal forces are. If you saw statics by now, you know that you can compute forces, you can compute center of masses, you can compute stresses, strain, internal forces, and all that is a force, is a vector. Okay, remember that a force is a vector. So it really depends where your coordinate system is. Now, if you want to find your center of mass, maybe you do want your coordinate system here, so that when you do a summation of moments, etc., you can have this weight of the airplane as an unknown. Okay, so this is for those of you who want to go to engineering. Make sure that you have a big picture of what you want the whole project to be. Is it a whole airplane, and then we're going to analyze the performance in a wind tunnel, so we're going to have to manufacture it? Is it easy to create a 3D printed version of it, or we're going to have to build part by part for the model to be tested? If this is assembly, each component will have its own coordinate system that has a reference to the main coordinate system, etc. So we'll talk about those details later. So as I said, every point that you create in your drawing will have a unique distance, a unique coordinate, okay? And that is with respect to your X, Y, and Z coordinate system. Later, when you go to mechanical engineering or electrical engineering or anything that you want to study with that requires science and engineering concepts, you'll know that this coordinate system is very important. The location of it is very important. So think of a satellite. You want that coordinate system to be at the sun, or to be at the earth, or to be the satellite itself, a moving coordinate system. Okay, so those are the things that you need to know before you even start modeling something big, where you want your coordinate system to be. Once you have your points, your surfaces are created within the CAD, and the lines are traced, and the body is created. So the files to export this thing are usually STEP, that I forget what it stands for, solid part, could be IGES. All these things mean something, but right now it's not as important what it means as to know that this is a standard format of exporting parts. Okay, you can have parasolid, and this is if it's bodies, right? Solids. Solids is important to know the difference between a solid and a non-solid, because this could be a hollow body and the volume will be void, equal to 0. But if it's a solid made out of aluminum or copper, then the volume is constant. And if it goes a chemical process, is not a constant, may be changing. The volume can be changing with time. Okay? All right. So for a surface, for a cloud of points, you can have something called STL. And this is usually what you are able to bring to a 3D printer. So again, what is your end goal? Is it 3D printer, or is it standard manufacturing by a mill, or is it just creating a solid body to analyze with a software to know where your maximum stress is? All right. So assume that you want to create a drawing. So your part is going to be manufactured. So that part that you created is going to be manufactured. You need a drawing. This, in technical words or in technical field, is an annotation. Annotations. So you're going to have annotation for the part, and you can have a single view, a top view, or a front view, or a side view. We'll talk more about those. You can have a single section to just show details about this section C. So right here is going to tell you the sections. And you can have other sections, section E, section D, etc. So let's start by the basics. The size of your drawing is standard. Okay, and this is usually A5 or A3. We'll go into, when we open AutoCAD, I'm waiting for everybody to have it installed. When we open AutoCAD, we'll see the different sizes that you can choose. So just a single paper, the size of a letter, paper type, or if it's a huge size that you need a plotter to, in a huge table to be able to see the details. Okay, so the first thing is to decipher what size is going to be your drawing. From there, you can choose your scale. Okay, because the scale, if it's 1:1, that means obviously that 1 inch in your drawing corresponds to 1 inch in real world. If it's 2:1, is 2 inches in your drawing is 1 inch in your real world, in the real world. 10:1 is the 10 inches in the, you follow the concept. So each company, each institution will have its own block where it's going to have the name of the company, it's going to have the the title of the part, the version. So if it's version 1, version 2, if it's the 7th version of the part, and then modifications are created to the 7th version. In that case, they're processing in a company that engineering change notice are taking in place, so that production knows that you're not following version 6, you're following version 7, which is the latest and greatest, etc. You have a lot of details here. So as I said, each company will have as many details as they need so that production gets all the documentation needed. Important stuff is for the manufacturing department to know if the tolerances are going to be standard or precise, or more than unique standards, or they're going to be custom tolerances. The units are also going to be displayed, and then obviously the drawing itself. So their minimal amount of data, there's just some minimal. You can put a lot of data, but there's just some basic stuff that is needed. The basic stuff needed is center, the diameter of a part or the radius, the distance between grooves, the thickness of something. So like here you can have the thickness of a chamfer or whatever. And you as a designer decide what units to, what measurements, what annotations to add, and what to leave as not. You want to make sure that your annotations are not redundant. In other words, if you are sizing this diameter in this view, you don't need to size it again in another view. Or if you're sizing this distance in this view, this distance right here, you don't need to size it again in this view. Okay, so that's why you create sections, so that details are performed in such sections. So this section obviously is only about this object. Okay, so they're giving you the distance between centers, and they give you the distance between, if this is an ellipse, they're giving you the distance between centers and the distance between the smallest radius. Okay, so this requires a distance, which is right here, and this is what I was meaning before. So you don't have to say that this is the same distance. That would be redundant. You only place it once, and then it's inferred. You can, the manufacturing company or the operator knows that this is the same as that. Okay, if you leave it undetermined, then by the rule is that the manufacturer will know that this is the same as a different annotation elsewhere in the drawing. That's why the difficult part is to know what to explicitly mention and what to implicitly, what not to mention. Because if you don't mention something, the manufacturer is going to still charge you per hour. So they're going to come back and tell you, you forgot something and that ticket's still running, or they'll assume it's something else, and then your part might not fit the assembly. So the difficult part is really learning the concepts of what needs to be annotated and what's not supposed to be annotated. Another rule of thumb is that you're always wanting to keep them as aligned as possible. This is just a tool that every CAD has so that it's easy to follow. And you want to avoid as many annotations crossing the geometry as possible. So that this one right here will be a no-no, but there's really not much room for anything else unless you had another section somewhere else where you put this one and then this one could be like over here. But definitely a rule that needs to be followed is that you can never cross annotations. You're trying to avoid crossing geometry, but it can be done. Just don't do everything like that. Just a few, the ones that are really crucial and you cannot really have a way to put it through. Like no matter what, this section, you're always gonna have to cross the geometry, but never ever cross annotations. This line is a big no. The same way that if you're gonna annotate this guy, you're gonna bring it out here and then put the number here. Never inside the geometry. And again, never cross the other annotations that you have. All right, so as I said, the drawing has different types of content. We mentioned points, surfaces, lines, which are also called vertices, and they are usually combined in 4 portions. The drawing itself, which is the part that you're editing with surfaces, with lines, etc. The information block, which is either in the drawing itself or either with in your CAD file. So if you open your part in your Autodesk or your SolidWorks or whatever software you're using, you can have notes and comments, and that will take, because sometimes you don't share the drawing, you share the part. So it's a living document. The part could be edited by many people, and that's why you have different versions, right? So that if version 7 didn't work, you can go back to version 6 and go start from there. There are zones where you can use for different sections and for tables and for like assembly notes, and the notes where you have comments or you have welding. We'll talk about that later, where you have symbols for welding, for chamfers, for types of custom manufacturing techniques. Okay, now when you talk about a drawing, you usually have 2 types of drawings: a 2D drawing and a 3D part. So let's start by 3D. So this is where it's called isometric. So when we open AutoCAD and we say go to the isometric view, you'll see what that means. It's just the 3D part in certain angle. So for instance, if you have a cube, the front view, and the cube is width equals 5, height equals 3, and depth equals 2. Let me see if I can draw that. So it's 5. So front view. How can I do that? No, let's do this one is top. This one is front. So from the top view, I'm gonna see the, let's see, 5 here, 3. Okay. Then this is aligned. Then we're gonna have from the top view, we're gonna see 5 and depth 2. So this is 2 versus this is 3. Because in the front view, you see width. This guy right here is width, so 5, and height, which is 3. Versus here, you still see width, but now you see depth, right? So this is still 5, just like here, and this is 2. The width equals 5. All right, you can also have a top view, either here or here. So if you do it here, the top view, sorry, not the top view, the side view, you can do right or left, depending, but if it's a cube, it will be the same if it's right or left. So the side view would be 2, height is 2, And then let's see here, what is your, this is your width, this is your height, this is your depth. Sorry, no, the depth is 2 and your height is 3. Yeah, this is your side view. You can actually, depending on your coordinate system, right? That's what really makes this part be decide what's the width, the height, and the depth is the coordinate system. All right. Again, we'll do this in AutoCAD so you can see the concept. But this is when you basically have only the sides or the, correct me if I'm wrong, I don't know if I'm getting myself confused, trying to talk, draw, and put everything together here. But my point being is that if you want, this is the 2D version, but the 3D version is the isometric itself, which is the 3D view. This. All right, and that would be the 5, and these would be your 3, and the depth will be your 2, etc. So this is the 3D view, and all those are the 2D view. Now, a 2D view that is very, very common is for electrical drawing. You know, electrical drawing, I don't know if you're very familiar with electrical concepts, but let's say you have your battery. So you bring your plus and your negative, and then they have arrows, and then you connect a resistor perhaps, and then a switch, and then you have I don't know, a solenoid or something, a valve. Okay, and then that is connected to your negative, right? Or if you have a PLC that is changing your, that is connecting to your, this is ground, you're connecting this PLC to your power, then you can have something like your power lines, which is your line 1 and your line 2, or your neutral, let's say if it's 120 volts. And then you have contactors, and then you have motor pumps, etc. Yeah, so this type of things, AutoCAD is actually pretty good at it.